Welcome to my presentation. This talk aims to bridge the gap between AI theory and the practical reality of modern development. It is important to note that artificial intelligence is not powered by a single programming language. Rather, it is built upon a layered ecosystem of languages, tools, and infrastructure components that work together. Most data science and AI learners will likely spend a career as a practitioner, using data science and AI to solve business challenges, rather than a researcher building models from scratch at OpenAI, Google, or Anthropic. However, understanding the engine room of AI is crucial. It demystifies how these tools function and provides a clear technical roadmap should you choose to move from applying models to the high-stakes world of AI research and development (R&D). In the current professional landscape, a sharp line exists between AI users and AI builders. Most data scientists fall into the former category, utilizing pre-trained models and high-level APIs to extract value from data. However, the systems they use are built on a complex foundation that prioritizes two competing needs: developer productivity and raw execution speed. Understanding this divide allows you to see why certain tasks, like training a model, are expensive and slow, while others, like generating a report, are instant. For those looking to transition into R&D, moving beyond the what of AI to the how requires mastering a specific hierarchy of programming languages that handle everything from user logic to the electrical signals on a GPU. Python remains the dominant language in AI development. It consistently ranks at the top of major popularity indices such as TOBE and PYPL. More importantly, it dominates in machine learning research, data science workflows, and model prototyping. Python's strength lies in its ecosystem. Libraries such as NumPy and Pandas are foundational for numerical computing and data processing, while scikit-learn powers rapid experimentation and traditional machine learning methods, including support vector machines, k-nearest neighbors, decision trees, random forests, gradient boosting, k-means clustering, and principal component analysis. Furthermore, PyTorch and TensorFlow are Python-first deep learning frameworks that support neural architectures such as CNNs and RNNs, as well as modern transformer-based models. Hugging Face's Transformers library builds on these frameworks to provide a Python-centric ecosystem for large pre-trained transformer models, including LLMs. In short, Python acts as the orchestrator of modern AI systems. However, an important clarification is necessary. When a deep learning model performs billions of tensor operations per second, that computation is not executed in pure Python. Python provides the high-level interface, but most heavy computation runs inside optimized native libraries, often written in C++, and accelerated through GPU kernels, commonly CUDA in NVIDIA environments. Python coordinates, lower-level languages execute. Underneath Python, performance-critical operations are typically implemented in C++. Many deep learning frameworks rely on C++ backends for tensor manipulation, memory management, and execution scheduling. When TPU acceleration is used, especially in NVIDIA-based systems, CUDA enables massive parallelism. GPU kernels handle matrix multiplications, convolution operations, and backpropagation steps at extremely high throughput. That said, CUDA is not the only path to acceleration. TPUs, ROCm for AMD GPUs, and other hardware stacks exist. Most AI developers never write raw CUDA kernels. However, those working on performance optimization, custom operators, or large-scale training systems benefit from understanding GPU programming concepts. Key GPU programming concepts include understanding the memory hierarchy, such as shared, global, and register memory. Parallel execution involves thousands of threads running simultaneously. Kernel efficiency is crucial, focusing on optimizing compute-to-memory ratios. For research and development engineers, GPU literacy is invaluable, even if direct CUDA programming is not routine. Modern AI is not only about models, it is also about infrastructure. Rust and Go are pivotal in AI infrastructure. Rust has gained attention for systems programming due to its memory safety guarantees and performance. It is increasingly used in performance-sensitive infrastructure, developer tools, and backend systems. For example, OpenAI's Codex CLI is built in Rust. Rust is particularly attractive for AI serving systems that demand safety and speed. Go plays a major role in cloud-native development. A large portion of the Cloud Native Computing Foundation (CNCF) ecosystem, including Kubernetes, is written in Go. Many AI platforms deploy models using containerized microservices, orchestration systems, and distributed services written in Go. While Python dominates modeling, Go and Rust frequently appear in production deployment stacks. The way we write all the languages mentioned above has fundamentally changed. We have entered the era of vibe coding, a term coined by Andrej Karpathy to describe a shift where developers describe the vibe or intent of a program in natural language, and AI agents generate the code. Tools like Claude Code, GitHub Copilot agents, and Cursor have moved beyond simple autocomplete. They can now plan entire features, run tests, and debug errors autonomously. In modern development, virtually no one writes code from scratch. Instead, the modern developer acts as an AI architect, using platforms like Google Colab for rapid prototyping and cloud-based agents to handle the grunt work of syntax. AI tools enhance development speed, yet human oversight is crucial. Developers now focus on prompt design, crafting precise AI instructions and architecture, making strategic system design choices. Code review ensures AI-generated outputs are accurate, while integration involves debugging and connecting components, maintaining the integrity of AI-driven systems. Besides Python, C++, and CUDA, there are other essential tools as part of the AI workflow. Most applied AI work depends on data extraction, transformation, and validation. In enterprise environments, data reside in relational databases and warehouses. Before training any model, practitioners must query, join, filter, and aggregate data. SQL is therefore often the second most important language after Python for real-world AI work. If you are building AI products, not just models, you will likely interact with front-end or web layers. In this case, JavaScript is an indispensable tool. In summary, the AI language stack is structured into three layers: orchestration, infrastructure, and core performance. Python orchestrates processes, while SQL and JavaScript handle data access. Rust and Go are crucial for infrastructure and deployment. For core performance, C++ and CUDA provide essential GPU acceleration. Each layer plays a unique role, from hardware efficiency to user interaction. In conclusion, while you may start your career applying AI to business strategy, the path to innovation lies in understanding the tools that make AI possible. If you are an applied data scientist, what you need are Python and SQL. If you are a machine learning engineer or an AI infrastructure developer, then Python offers you the flexibility to build. C++ and CUDA provide the power to scale, and Rust and Go ensure that your systems are safe and reliable. More importantly, the rise of AI-assisted coding means that your value as a professional is no longer tied to your ability to memorize syntax, but to your ability to solve problems and steer AI tools toward a desired outcome. Whether you are a practitioner or a future developer, mastering this polyglot stack is your key to staying relevant in an AI-driven economy. As you look toward your career, where do you see yourself on this spectrum? Are you drawn to the application side, using these tools to transform business? Or do you feel the pull toward the R&D engine room, building the infrastructure of tomorrow? Furthermore, how will you balance the traditional rigors of programming with the new frontier of vibe coding? There is no single correct path. The industry needs both architects and pilots. So what do you think? Please leave your comment here. If you found this breakdown helpful, feel free to like and subscribe for more insights into the evolving world of data science and machine learning. Thank you for watching. Goodbye.